Okay, so today we have Aziz Kharoof from University of Haifa, and he will talk to us about higher order Toda brackets.
Thank you very much. So I have to share you just a minute. Confused. Sorry. Okay. Now you see?
Yes.
So, hi everyone, and sorry for letting. I want to make it full screen. Here. Okay. Now you can see. Okay. So let's begin. I want to talk about higher order Toda brackets. First of all, I want to define the primary Toda bracket. So given a sequence of maps, one can imagine that it's all what I do here in topological spaces, okay? The maps are continuous maps, the objects are topological spaces, but what we do here, we can do in any pointed model category, okay? So one familiar with model categories can think we do this in general model category, pointed model category, of course. Okay, if we have a sequence of maps like this, where the composition here, you see the mouse, yeah? You see the mouse? I want to be sure that you see the mouse.
Yes.
Yeah, it's okay. Thank you. So if the composition here is null homotopic and the composition here is null homotopic, and we choose some null homotopies for this composition and for this composition, then we get the following. We have this null homotopy F for the first composition, and we can compose with H and get a map from the cone of X to W. In the other hand, we can compose this null homotopy, the null homotopy for this composition, GH, and compose this with F, or with the cone of F, of course, because the domain here is the cone of Y, and get another map from the cone of X to W. So both maps coincide at X, okay? At X is we have the same formula, it's FGH. So actually we get the map from the suspension of X to W, okay? We get the map from the suspension of X to W. It's the Toda, okay, sorry. Yeah. So this maps with the null homotopies induce this map from the suspension of X to W. This is my notation for this map. It's not depends, it's obvious that it's not depends only on the maps, but it depends the choices of the null homotopies. Okay, this is the Toda. So Toda firstly defined by the mathematician Hiroshi Toda. So it's named after him. But he used it to calculate homotopy groups of sphere. What he did, because you see here, I can explain something about it, because what we see here, I don't find the pin. Why? Just a minute, sorry. I can write here, but I don't know why I don't find the pin. Maybe you have to make me co-host to do that or not?
Okay.
Because here I can annotate, I want to do that.
See.
Okay, sorry, what are you trying to do?
I want to write something. I want to write here, but I don't find there is annotate. I can do, then I can maybe here. No.
Okay, let me see.
I don't think you can do it unless.
No, I can do. Why? But last time I did it in the graduate seminar.
Okay. But this is a different account. It's
a different account, so yeah. maybe I can. Okay, so maybe I do share, say, okay, with someone, okay, Okay, now I can write here. You see, yeah, you see it. I want just to explain how something about Toda. That's what you asked me also last time. What Toda did.
Okay,
He
so
did maybe.
sorry, Aziz, I just made you co-host. You can try.
Now I try.
Yeah, you can try. If it doesn't work, I don't know what else to do.
No, it doesn't work. Maybe it's my fault. Okay, I can maybe exit from this. Then, sorry again. Maybe if I exit here, maybe I can write here now. I share you. No, I don't see it where I can annotate. It's all the time I see it here. Even I teach, I do it all the time, but I don't see it.
There's a pen there.
Something that okay. Maybe when I can use this, maybe here I can write. No, I can here write. Okay, by this one. This one. No. Okay, sorry again. Just a minute. Sorry. Okay, let me do this. Let me do this. I want to share you again, and then I can write here. Okay, I want to explain now. Just you see now the whiteboard, yeah? You see it. So I want just to explain you what Toda tried to do when he defined the Toda bracket. He takes some sphere, for example, SM, and take also here also spheres. He takes some spheres here, where the composition here is null homotopy, and take another sphere here, for example, SN. From maps he know from sphere to sphere he get, because in Toda we get a map from the suspension of this, but the suspension of this is SM plus 1. So he get a new maps from sphere to sphere, okay? That's what he tried to do, and all the time he do new tricks, and it's something sorry, complicated what he did, but that's what he that's the reason why he defined the Toda bracket as a homotopy operation, that he can build a new maps from sphere to sphere from non-maps. Okay. Okay, I want to share you it again. This. So, okay, Toda, the first one, he defined Toda bracket, but then afterwards, Frank Adams used it as a differential in spectral sequences. But I want to show another application that Toda serve as obstruction to rectification linear diagram. What I mean by this, if we have the following linear diagram, and the case of Toda, where the composition here is null homotopic and the composition here is null homotopic. And then if we have a null homotopic Toda for some choices of null homotopies, F and G, we can rectify. If we have this, we can rectify this linear diagram. What I mean by rectifying this linear diagram, I mean, I can't annotate here. You know, if we have two maps where the composition is null homotopic, if here we have two maps and we choose null homotopy, for example, the composition is null homotopy, so we can rectify it. We can change it up to homotopy by zigzag of weak equivalences. Okay. And here we get another representative of the same diagram where the composition is not just like here null homotopic, but it's exactly zero. Okay, we can do this if we have two maps, but if we have three maps, where the composition here is null homotopic and the composition here is null homotopic, not always we can do that. We can't. I will give you an example, but we can't do it always. But what the abstraction to do this is the Toda. So we have many values of Toda. Every choice of null homotopy here, F, for this composition and null homotopy here, we get Toda. Every choice. If for some choice is null homotopic, so we can rectify this. Okay, we can rectify this. We can find a representative for this diagram. A homotopy represent other, the homotopy class of this diagram, where the composition is exactly zero here and here exactly zero. Yeah, this is the theorem. It's if and only if, yeah, is if and only if. Maybe here the important one that this says that if we have a null homotopic Toda, then it's rectifiable. Now I want to show you an example in chain complexes. We have this diagram in chain complexes. One can see that the composition here, it's not zero, but null homotopic, the composition of this map with this map. It's not easy for me because I can't write here. I want to write here, but maybe you can imagine. We can choose here 0 and 1, okay? 0 and 1. And this will be a null homotopy for this composition. And here, one can choose here 1, so 1, 2, it's 2, and here 0. So it's null homotopy for the other composition. And if someone calculate, so the Toda, so he got a map from the suspension of this to this. So it's going up here, and we get the map from this to this. We get, if we choose what I explained, this null homotopy, what I said before, we get the identity. Okay, sorry, I can't do the calculation, but because I can't write here, but it's okay. You believe me? Yeah, you believe. Okay, so we get the identity. Okay, here the Toda will be the identity from this chain complex to itself. The suspension of this, it's the same. We get this Toda. So we didn't get the null homotopic. The idea is not null homotopic. So what it's told us that it's not rectifiable? No, because we back to the theorem. The theorem told us why I can't do the here I can't do that. Okay, the theorem told us that if there is some choices with a null homotopic Toda, so we don't know, we just choose some choices. So we have to look at all the choices. So here we have to look at all the choices of null homotopy, all the todas, okay? And ask ourselves if there is one null homotopic. Here we can do that. In chain complex, it's easy to do that because we have the following fact, okay? Here I denote all the todas by this notation, okay? When we run over all the choices of null homotopes, here this is null homotopes. So this is the set of all the todas. It's not all the homotopy classes of todas, okay? So we want to find 1, 0 here. If we have 1, 0 toda, 0 homotopy class, so we get the diagram is rectifiable. If not, no. So no, because it's if and only if. Here we have the following fact in chain complexes that this set, it's ecoset. It's you know that this set, it's in the homotopy class of the homotopy classes of map from the suspension of X to W, but in fact it's a coset in this group, okay? In general, in topological spaces, for example, it's not, it's a double coset, okay? It's not, but here it's coset, and it's easy to calculate these things. It's not, I calculate this, and this is 0 in our example, okay? So this is 0. Here, maybe I have to put here the homotopy class of H, not H itself. But okay, I don't want to confuse you, but it's the homotopy class, and here is the homotopy class of this. It's okay, so it's 0. This is 0. I calculate this is 0, and this is 0. So we get just the identity. You know what I mean here is some representative of Toda, okay, for some choice of Toda. But we did it, so we get the identity, and here 0. So the only Toda we get is just the identity, so we don't have any null homotopic Toda. So the above diagram, it's not rectifiable, okay? Okay, so it's not my goal in my lecture. I want to extend the definition of Toda. I want to show you how people extend the definition of Toda, and how we can, in 2 ways, and how we can show that that 2 ways it's the same, and to define a new, to describe a new way to define general Toda. But before this, I want to do another thing. I want to define the primary Toda, what we did before this. I want to back to this. This is the definition here. Ah, sorry, I'm not in this. Ah, here. This definition, the Toda, I want to define in another way, okay? Here. So I want to define Toda in terms of homotopy cofibers. So if we have 2 maps and null homotopy between for the composition, we have the following square, okay? We have the following here, the inclusion from X to the cont. And I can apply the homotopy cofiber here in this side, okay? Sorry. And we get the map from the homotopy cofiber of this, which is the suspension. You know what I mean by the homotopy cofiber? I mean this model of the homotopy cofiber. Sorry. I can write here. This, if I have a map, this is a map, for example, F. So I mean by the homotopy cofiber, this model is a push out of this. Okay, so this is a cofiber. Is a push out of this. And this is the homotopy cofiber. But sometimes I can choose another model for the homotopy cofiber if the map here cofibration. So for me, it's the same. Okay, it's not in general. It's in proper model category, but it's okay. So it's equivalent, and this is a model of homotopy cofiber. Or sometimes if the domain here it's contractible, so we can choose him to be here's the con, and my homotopy cofiber will be the y. The push out of this is y itself. Okay, so this is the push out of this. So I will use just this is 3 models of the homotopy cofiber. So back to our PDF. So here I have this square. I applied homotopy cofiber. I get a map from homotopy cofiber of this to homotopy cofiber of this. Okay. In my model. So the homotopy cofiber is the suspension here, and the homotopy cofiber of G. I denote it by this notation. Okay. And we can do the same, but in the other direction. And we get the following. Here you see I choose the homotopy cofiber of this because this is contractible to be Z, and I get this map. So if we have the situation of Toda, when we have this sequence and a null homotopy for this composition and a null homotopy for this composition, then we have 2 squares. We have 2 squares, not just this square. We have the square of this composition and null homotopy G. So I want to compose the alpha that induced from this with the beta that induced from this. Okay. Okay, region. It's okay. So I get alpha from this square, and here, not to be confused, the beta it's from the other square. Okay, how I can, yeah, beta from the not the same square, from the square of G, H, and this G. So they have the same, the codomain of this is the domain of this beta. Okay. And if I compose alpha with beta, I get a map from the suspension of X to W. So one can check that it's the Toda. This is the Toda. The same. So this is another way to see the Toda, the definition of Toda using homotopy cofiber. I will use it later, and I will explain it again when I use it later. So now we're going to do what we want to do in this talk, to see the higher order Toda bracket, how people define the higher order Toda bracket. If we have longer sequence, okay, longer, not just 3 maps, 4, 5. I'm going to do this just for 4 maps, but if someone understand this case, so can understand the general case. Okay. So in 2 ways. The first way is a cubical definition. It's using cubes of one can define this in a category that enriched by cubical sets, or even simply shell set, but it's okay by cubical sets. I will define it. Okay, I will explain it later. This is one way, and we have another way, recursive definition. Using alpha beta, I defined before, and here we can generalize the rectification theorem. You remember we have this. I come back here to this theorem. So we know that Toda is the abstraction of rectifying this linear diagram. But what if we have a longer one? So what is the abstraction to rectification there? So it's the extended Toda. Okay. But people proved that in this case, in the case of recursive definition. This case, even it's enough to be in triangulate category to define this in recursive way, okay? Okay, so what I said before, we're going to describe these two definition in the situation we have four maps. Okay, let's go now. Cubical Toda bracket. Okay, I wanted to write it here, but now I want to open a new whiteboard and describe the cubical one. So if we have four maps, X, G, K, V, and we have a null homotopy here, null homotopy for this, and a null homotopy for this, and a null homotopy for this. So we have the following. We have this F, and we have a null homotopy, this composition, sorry, F with G, and we have a null homotopy for this to a constant map. Okay, the star, it's a constant map, but my map is point, and this is the homotopy between them. And we have a null homotopy from the composition GH, null homotopy G with the constant map. And how we build the first Toda, we compose this with, you remember at the first beginning, we compose this with here. We compose this with H and compose this with F in this side. Here, the con of F I have because it's con, okay? And we glue them together, yeah? Because here it's common here in this side. So we get this. Sorry. From both, we get this. And here we have F, G, H. And here we have C, F, G. Okay. And here is constant map, here is a constant map. Okay, we have the same here because we have two Todas here, two primary Todas. We have this Toda and we have this Toda from this sequence. Okay, so we not have just here, we have from the other sequence. So here G replace the F, so we have this G, and here K, let's replace the H, okay, extension. And here we have the composition G, H, K here. This is star, it's not the same, okay. And here we have the con of G composed with the last null homotopy Toda. Okay, so now to build the higher order Toda, it's not enough to have this. We have to have, we must have a null homotopy for this and the null homotopy for this Toda. So okay, we have to fill it for a map from the double con. Maybe I choose another from, if we have a map from the double con, sorry, a map F2 from a higher, a second order null homotopy to W to fill it. Okay, so here it's one, okay, this F2, and we must have a null homotopy for this G2, second order null homotopy from the double con to V, double con of Y, of course. to V. Maybe I choose here another, okay, to see this F2 here, and here G2. And then we compose like we did here. We choose it, and then we compose with, here we compose with K, with the last one, and here we compose with F. So let me do that. So I compose here with everyone with K. Oh, sorry. I have to compose, this is a cone of F with G, yeah, with K, and here with K, and here I compose with F. So here I compose with F. Here it's not exactly with F, with it because it's a G here from the cone of Y to V to W. So I have to get the cone of F here. So with the cone of F here, and here with the cone of F, and here from the double cone of F. It's the same F, but in all the cone, okay? And then we can glue because we have here common side, yeah? Where is the common side? This side, you see? This side and here, the same. Okay, so we can glue them together. Okay, so we must have two to do the higher order Toda bracket. For 4, we must have 2 second order null homotopies. It plays the role of this null homotopies in the primary Toda bracket. Okay, I want to back to my PDF. It's here. So we get this. We glue them together in this side, you see, this and this. And we have another side that it's not coming from, we have another map from the double cone to V, to the last one, but it's not coming from a new second order null homotopy. It's coming by composing first order null homotopies, okay? You see, this one, and I come back there to my whiteboard, yeah, you see, if we compose this with this, not this exactly, it's F, it's a cone of F with H, so we get the map from the double cone to V, and the side, it's the same as the sides here. So we get a map from, you imagine what it is, this is one double cone, one double cone, one double cone composed, the other side, it's just the points. So I denote it by L2x. This is, in fact, it's equivalent to the double suspension. Okay, the domain here is equivalent to the double suspension. Okay, so this is the cubical definition. We see that we can do it not in just in topological spaces or in pointed model category. We can do it in enriched, in category enriched by cubical sets. Okay. Okay, let's go to the no, before I'm going to the recursive definition, I want to do some notation just to tell that we have here the system of the Toda system for cubical. What I mean by Toda system, I mean all the maps and the null homotopies I need to build the Toda. For example, for the case of 4, we must have the maps and 3 null homotopies. First order null homotopies and 2 second order null homotopies. You know, so one can imagine if we have 5 maps, so we must have 4 first order null homotopies, 3 second order null homotopies, and 2 third order null homotopies. You see, so this is called the Toda system. Okay, the Toda system. It's all the information we need to build it Toda. And I now use this notation for Toda because it's, you see, instead of this, sometimes I will use this, okay, to be this. I have here the system, the Toda system. I apply T, the Toda. This is the homotopy operation. Okay. Later, why I do that? Because later we will prove, we will first of all define equivalence relation between Toda systems. There is, for example, I can choose another here choices of null homotopies, and we ask where it's equivalent. What we mean by equivalent, we will explain later, but we will define a relation between Toda system and such relations that if two Toda system are equivalent, then their Todas are equivalent. Okay, we'll explain this later. So let us go now to the recursive definition. Maybe it is easier to explain the recursive definition. For the recursive definition, if we have four maps, and so we have null homotopies, F for this composition, G for this composition, H for this composition. So we have the following squares. I can choose this square to be cofibrant squares, okay? We can do that, replace it by cofiber square. I need this because I want to apply just the cofiber, not the homotopy cofiber, the model of what I did before of the homotopy cofiber. You will see later why. So, okay, so I have this. Now I want to take from this square just the alpha of this square, and from this square the alpha and beta, what I did before, and from this square just the beta. Why I do that? Because here, if you remember, if we compose this alpha with this beta, we get the Toda of this, okay, of the first three maps. And if we compose this alpha 2, this one from this square, with the beta from this square, it's coming from this, we get the Toda for this sequence. So now we ask the Todas to be null homotopy. So we choose null homotopy for the Toda. This is the Toda for the first three square, is three maps, sorry, this. So this is a null homotopy for the composition for the first Toda. And we have another first order Toda. So I choose a null homotopy for this. So you see, we can define just, we don't need just a null primary order null homotopy. We need another second order here also. We need second order null homotopies. Then we take the alpha of this square, this alpha of this square, where we apply here the cofiber of this and the cofiber of this. Okay, so we get from the double suspension to cofiber beta, and here we want the beta of this square, so we get the map from homotopy cofiber of this alpha 2 to the homotopy cofiber of this, and we can compose. Why? Because the homotopy cofiber, the homotopy cofiber, it's a cofiber here actually, but because everything is cofibration, so it's the same. So here we have the same. That's what I use here. I make everything cofibrant, and I apply cofiber instead the model of homotopy cofiber I did before, because I want this fact that here we have square, and I apply this cofiber in this side, and then in this side, when I take the cofiber of this and the cofiber of this is the same. Okay. So I use that fact, and I can compose them and get them out from the double suspension to the cofiber of G2, which in reality it's equivalent to V. Why? Because it's, you see, because it's this map is a cofibration, and this one is contractible. Okay. it's an improper. It's improper model category. It's okay, but it's okay in topological space, chain complex, simplicial sets. It's okay. So we get something. We don't get here the V itself like we get before, like we got before, but we get something equivalent to V. Okay, so this is like one can imagine how we can continue. Okay, now if this composition is null homotopy and I have longer sequence and the other is null homotopy, so I can choose. Okay, I can I get two squares and I take the alpha of this and the beta of this and compose together. Okay. We also define the recursive Toda system. It's the same. All the null homotopy we need first order null homotopy and second order null homotopies we need to define this, to define the Toda, the recursive Toda. But we see it's not the same. The primary order null homotopies is the same in the recursive system and in the cubical system we defined before. But the second, no, it's not the same. We will see later. I will emphasize that point later. Okay, so I use also this notation for Toda now. But you see, I used all the time with tilt. It's called tilt, yeah? So I can tilt for the recursive and for the cubical without this. Okay, here also we later define the equivalence relation between Toda system. Okay. And here we have this theorem. If we define if we have a recursive and recursive Toda system where the Toda will be null homotopic, then the underlying this diagram it's rectifiable. Okay. Okay. Now we want to emphasize the obvious difference between the obvious differences between the two definitions. Okay. So first the construction, yeah. One of them we can here maybe I did it. I want to back to the first definition, the cubical. Maybe here when I did it in my whiteboard, I did it in like recursively way, but it's not recursive. One can give you all the homotopies and you compose and glue them together. Okay, all these maps. You compose some maps and glue them together and you get this. Okay, so this is the way, the construction. But the second, the recursive, it's recursive way. Okay, so there is the difference in the construction between both and different of second order null homotopies. We have the different second order null homotopies in the cubical Toda system, the cubical definition. We need these models of null homotopies, and in the recursive we need this. So it's not the same. And the Toda itself, we don't have the same domain and the same codomain. We know that this is equivalent to this object equivalent to this object. And as we explained before, that V, the last target, okay, it's the same equivalent to this. But it's not told us that we have here equivalent maps. Okay. So now to do that, to show the coins that two definition agrees, it's in some sense I will explain later, but to show that I need a new definition. Okay, it's the diagrammatic definition. So let me start with this. Yeah, it's just a minute. Yeah, I still have it. Okay. If I want to back to the primary definition of Toda, I want to define now from the first definition of Toda, I want to show the definition in another way. Okay, so now I want a new page. So if we have this case of primary Toda and two null homotopies, we have null homotopy F for this composition and the null homotopy G for the other composition. So I want to look it as separated too. Okay, I want to look like this. So because of the null homotopy, we have two squares here. We have two squares. This squares because of this null homotopy here, and this null homotopy here. We have two squares here. In fact, this square x to y, g, z, and this square y, g, h, and here it's g. But I want to change to how to make them match. So I want to rotate. It's not exactly rotate. I don't know what it's in English it's called, but I change this how it's look. What I did here, I want G to be here and here Y. Sorry, here's the H and here the G. Okay, it's the same square. See Y and here Z and here W. Why? Because now I compose them. I can look at this as a map of maps. Okay, a map from here to here, and here we have from this knowledge that from this data that I have in null homotopy here, I get a map from G to this null homotopy, and I can compose them together. Okay. And we get this. Here, what I did, I organize all the data I want to know about the null homotopies in one diagram like this. I want to do now the same for the case of 4 maps, okay? When we have not just 2 null homotopies, we have 3 null homotopies, first order null homotopies, and we have 2 other second order null homotopies, okay? I want to do the same. Okay, so this is the first situation. Now I'm going to the second order Toda bracket. It's when we have 4 maps and 3 first order null homotopies and 2 second order null homotopies. So we can get the same diagrams as before from this, because I can't write here, sorry, but from this 3 maps and the null homotopies F and G, we get this. And from these 3 maps, G, H, and K, and these 2 null homotopies, G and H, we get this, okay? And by this second order null homotopies, we can make here a null homotopy for this composition, okay? I come back. We can, oh, sorry. We can think about it as a composition of two maps, okay? maps between maps. And we have here a null homotopy for this F2. I put here F2, and because, and if someone says that the diagram here it's commutative, it's the same to see that F2 is the second order null homotopy I chose before, where I still have this or not. Here is the same F2 that fit here, where one side it's F, this F with H, and the other side it's, before I compose, okay, this. So we see here, we can return and see here, to see that is the same. You see, in one side of F2, this second order homotopy, in one side it's, in this side, it's F composed with G, and the other side, here is the other side, so it's this. Okay, and we can do the same by G2 to choose a null homotopy using this null homotopy for this composition. And now, as we have before, we have here a common side. We can think about it as a map from cube to cube, yeah? From this cube to this cube. And here I want to think about it as a map from this cube, which is the same, this cube to this cube. A map from this cube to this cube. Okay, so we get the following. So we can compare it with the primary one. Okay. So here's the cubical Toda system. This is the cubical, the case of the cubical Toda system. So we can encode it, all the information of the null homotopy and how they act together by this commutative diagram. So here's the idea. It's come from here because we candidate it's a primary situation, but in the second order situation we can do it also, and in every higher order situation we can do it. Okay, and how we can get the Toda from here? That's the question. How we can? Okay, it's just to encode it the Toda system, how all the maps and the null homotopies. Here we see, because this cube is, because this square is commutative, so we know that this F capital, it's a null homotopy for this composition, and we know what what, for example, G2. What is G2? G2 have in one side, it's in double cone, it's the second order null homotopy. In one side this, and in the other side it's here this. Okay, this composition here, it's a cone of one map, so the maps it's a cone of H, I think. Okay. So, but how we can get the Toda from this? We remember how we got the Toda here. How we get the Toda? By applying the homotopy cofiber. So we can do the same here and applying the homotopy cofiber here. So homotopy cofiber of this is a double suspension or something equivalent to the double suspension to the homotopy cofiber of this cube. So we will do it later. Just I want to continue here. So I wrote it what I said now. Okay, maybe I will use this notation. You know, because I want to use this notation later. So here it's I mean by this one. Okay, we can generalize this for the general case, and this in the middle, when we have all the middle maps and the middle null homotopies here in the middle. Okay, and this by this notation. Okay, you don't have to remember this, but just now I want you to remember, because now we can define the relation between to the system. Now we can define why, because I encode all the Toda system in diagram. Okay, so here I have Toda system, one Toda system. I can have another Toda system, not the same maps, not the same null homotopies. Okay, another Toda system. And how I can say that two Toda system are equivalent if they are equivalent as a diagram. If there is, yeah, here is the definition. Two Toda system are equivalent if the induced diagram, the corresponding diagram are equivalent. As the diagrams, we have zigzag of equivalences between these diagrams. Okay, and we can get the following result, that if we have two equivalent Toda systems, then the corresponding Todas for everyone, this is the Toda, this is one, okay? The Toda for this Toda system is the same, okay, equivalent also. Why we get this? Why? Because we have, because it's what I explained before, how we get the Toda from the diagram. We apply the homotopy cofiber, the homotopy cofiber here, the homotopy cofiber is a homotopy cofiber here, and we compose. We did this definition before of the Toda, alternative definition of the Toda. And we can do the same here for, we can do the same here for this diagram. But we have to know what it's the homotopy cofiber of cubes, not just for maps, because here we have cube, square. In general case, we have any cube with general case. So the cofiber of square is this, okay? The colimit of this. And the homotopy cofiber of square is this, is the colimit of this, okay? You can imagine why we defined it, because for example, I give an example, the homotopy cofiber of this is exactly the L2 we get before, you know, this is like a cube, but it's points in the three sides. And then one, three sides is cons, and it's the other side is a point. Okay, why, and we can do this as an exercise. And you know, if here when we get here, when the cofiber, it's exactly the homotopy cofiber here. Sorry, we run on. Where the cofiber is the same. If this square, it's cofibrant square. Okay. If this square is cofibrant, then the homotopy cofiber and are equivalent. The cofiber and the homotopy cofiber of square. So now how to get the Toda? We are applying the homotopy cofiber of square in this. So from, we have then the inducement from the homotopy cofiber of this to the homotopy cofiber of this to the homotopy cofiber of this. We get the same alpha and beta, and we compose them and get the Toda. Okay. Here I choose, like before, I choose the homotopy cofiber of this to be just the last one, because everything here is contractible. And here we get the cubical Toda system. So for the cubical Toda bracket. So for the cubical Toda bracket, we can do it in another way by diagrammatic to encode all the null homotopies in diagram like this. And then to apply the homotopy cofiber of square. Okay. Now, can we do that for the recursive one? This is the question. Can we do that for the recursive one? We can. So I don't expect now, if we have this null homotopies for the recursive Toda system, we can get this. So I don't expect you to follow everything here, but I want you to know the fact that we can do also diagrammatic for the recursive, but it's not the same. You see here, it's we have many points here. But you can see here, we had cons here instead of these points before in the diagrammatic description of the cubical Toda system. Here we have point, and not the same. It's not the same, but it's important to know that we can encode all the information of the null homotopies in one diagram like this. So, and if we apply the cofiber here, if we apply the cofiber, then we get the recursive Toda bracket. Okay. If we apply the cofiber, not of all the cofiber, the map induced from the cofiber of this square to the cofiber of this square to the cofiber of this square, we compose and we get the recursive Toda bracket. Okay. Okay, so now we see, maybe we feel now why it's we have the how we can go from one definition to another. How if we have cubical Toda system, how we can go to recursive Toda system and get Toda there. Okay, so how we do that? If we have a cubical Toda system, so we can encode it in diagram like this. And we can apply here just the cofiber of this side, cofiber of this. I do the cofiber of this, the cofiber of this, the cofiber of this, and then no, here I do the no, I make all of them point. You can see here what I do. Okay. So and we can get this cofiber. It's exactly the cofiber of this square here. And here, this is exactly the cofiber just of this. And here is just the cofiber of this. So we can get a diagram for the recursive Toda system. So from here again, from cubical Toda system, we can get recursive Toda system. Okay. In diagrammatic by applying this. Okay, it's hard to see why we do this specifically, not this. Okay, but now we can get equivalence between the Todas, because the Toda of this by applying the homotopy cofiber, and the Toda of this by applying the cofiber. And because we choose everything, if we choose here, we have to choose, because the definition for a general cubical Toda system or general the null homotopes I don't have everything here to be cofibrant, but if we choose this diagram to be cofibrant, then the homotopy cofiber equivalent to the cofiber, and we from this diagrams we induce this diagram, okay, between Toda. So if we have Toda system, cubical Toda system, we can get a natural way. Why? Because I did it a natural, I apply a natural operation. Okay, cofiber here. Here's a cofiber. Okay, so as to get a recursive Toda system. So we get it's in a natural way. Okay, I'll perceive the equivalence relations. Okay, and what if we have a recursive Toda system now? How we can get a cubical Toda system? It's by cofiber replacement. We choose a cofiber replacement. So, but not every. I want here to stay still the same x. I want here to be with the cone of x. For this, for example, I can choose this. For this cube, I can choose this to be cofibrant replacement, and then I can continue inductively. I can continue to choose. Here I choose the same map. Here I choose the cone of f instead this. Yeah. And here no. Here is a choice to choose this. It's a choice. Here everything I did here it's natural, but here I have to choose something. How I can choose this? It's a choice. It's one can get by this is the lifting of the. We have the lifting property in model category. So and we continue. Here we can continue naturally, but here we have a choice of this map and this null homotopy and this. Okay, we have choices here. Okay. And then we get, so we have the following theorem, but you see it's not the same because we choose. It's not, I didn't, then we have cubical Toda system, but it's not functorially, okay? I didn't denote it by R or something, okay? So if we have recursive Toda system, we can get, we go to the diagrammatic and we do a special cofibrant replacement. Then we can diagram for a cubical Toda system. So we have a cubical Toda system, and this is a relation between the Toda is with equivalent Todas. Okay. So that is, yeah. So, okay. I finished. Okay. Sorry if I didn't explain it too much good, and
Thank you.
because you know, I don't have this annotate. I didn't expect it. Sorry. So thank you for listening. I'm sorry again.
Thank you. Okay, so are there any questions?
My English. Sorry for my English.
No problem.
Not too much, but yeah. Sorry.
So are there any questions for our speaker?
Yeah, can I just ask a question?
Yeah, of course. Yeah.
Your notion of, I think you called them recursively defined Toda brackets. Is that equivalent to Joel Cohen's notion, or is it slightly different? I mean,
Which one?
really
Which
just
one?
asking for clarification.
There's a V couple.
Again, you can repeat your questions?
Could you just say, are they recursively defined Toda brackets equivalent to Joel Cohen's notion of Toda bracket? I mean, it sort of looks similar, but I'm not sure it's exactly the same, is it? Or is it?
As John, what?
Joel Cohen.
Joe Cullen, Toda bracket?
Joel
I don't
Cohen.
know. No, I don't know this.
Well, he wrote a very important paper in the late 60s on decomposability in terms of Toda brackets. I've forgotten the
Really?
title.
No,
It's
I
called the
don't know.
decomposition of stable homotopy.
Uh-huh.
The definition, which is a recursive definition. I'm not quite sure if it's what you were using or whether it's different.
Really?
Yeah.
You know, this is a recursive also Franklin, and they use this in triangulate category. So in the recursive, you know, we need just the homotopy types of the maps, and we need the cofiber sequences for the recursive. We need just this.
I mean, one of the reasons I'm asking is that the issue of indeterminacy.
Yes.
Quite subtle. There are some lecture notes by George, and he points out that even for the triple Toda bracket, the indeterminacy in Cohen's definition is not the same as in the Toda definition. So
Really?
when it comes to indeterminacy, there's a much bigger question, I think, about if you give different
for the primary Toda bracket or for the higher order.
No, well, in Whitehead's notes, he points out that the Toda notion has bigger indeterminacy than the Cohen notion, even for triple Toda brackets. Now, I presume when you get longer and longer, you know,
yes.
if you're using one definition, you don't necessarily get the same indeterminacy.
Yes, no, indeterminacy, I try to do that, and even my advisor and some of the students try to do that. It's not the same. We don't get something beautiful for the higher order to the brackets and indeterminacy. No, not just the primary. No.
Right.
No. We thought we can get something.
I mean, the other issue is, I mean, things like matrix Toda brackets. You know, there are all sorts of literature on higher order Toda brackets.
Really?
And again, you know, if you give a different definition, in the end, I think the question of indeterminacy is one that needs to be nailed, because if you're doing it by different approaches, you may well get different answers. So this is something else. I really am not sure what you can say about this. I mean, maybe you know.
Can you send me by email what you?
Yeah, I can send you. Yeah, I can refer you to them. Yeah.
You sent me some email for my article, maybe for you. You sent me some email
Did I?
You remind me to do something to, I forgot to send my email.
Okay, well, I'll send you the
Thank
link.
you for that. Yeah, I want,
Yeah.
no, I want to thank you for that because I just now.
I forgot what that was. Sorry, it's a while ago.
No, thank you.
Yeah,
Where
all
is
right.
the chat? I don't find the chat here. I don't find anything.
Hold on.
Where is it?
I can email it.
Here
to
is a chat. Yeah, here's
yeah.
a chat. This is my email. Yeah, it's my email in the chat for everyone. Yeah. It's Aziz Sketch.
Sorry, which is your
or maybe
email?
I send you email to remind you. I know.
Oh,
your
yeah,
email.
yeah. Okay, no, I've got that. I'll send it to after the talk. Yeah.
Thank you. Thank you. I send you email also to remind you. I know your email.
Yeah. Okay.
Thank you.
So
Another question.
yeah, I just sent you an email on what we. So maybe Özgün has an opinion of this. Throughout the talk, I think this topic is screaming derivators. Like maybe people did these things.
Yes.
In derivator theory, but
in the diagrammatic you mean, or just the?
Yeah, like I mean, as I told you, I'm not expert in the subject, but so derivator theory is something like, I mean, a derivator is something which is kind of less than an infinity category, and but it has enough information. I think, like basically, think about it like this: like it's an object which, for example, if you have a model category and you record all the homotopy coherent diagrams in the model category, and they're homotopy categories, right? So this is enough information, I mean, for you to talk about cones and things like that, and the equivalences between these diagrams, most importantly. So I mean, just by intuition, I
you
think,
feel that
I very strongly feel that
because I encoded the relation between null homotopy in one diagram. Why you do? Okay.
Yeah, and I remember from the how can I say, from the users of derivators, they told me once that derivator theory is very good for when you have homotopy commutative like squares and cubes and things like that, which is precisely the kind of diagram you were considering. So just saying, I sent you
I didn't have the time to do that, but
yeah, I mean, maybe
I lost what you said me last time. Your email,
So
okay, now it's okay.
Yeah, I
maybe we can discuss also.
Yeah. It could be. I mean, could be interesting. Like maybe people have done that kind of stuff. I haven't done any research or anything. It's just this time I attended this derivator event, and just from my recollections, not anymore from me.
I think the recursive definition is more about the derivators, because it's you can discuss rectifications and stuff.
Yeah.
I was actually wondering, is there a similar theorem, a rectification theorem for cubical version? Because I mean, how do you rectification?
Yes, I can explain to you. This is, if you have if you have a square and you can put, this is a question also people asked last time. It's here. If we have this is this square, you can rectify. Okay, it's the same what I said before, that this, if this is non-homotopic, this is non-homotopic, so you can rectify it. Okay, you can, and it's the same because you rectify in one side. It's the same to it's stay with the point, but it's homotopy commutative, but you can make it commutative, okay? But for what you ask for a cube, example you have here, you for the cube, not always you can rectify. And we proved it here. We proved because we proved that we showed example that the Toda we can rectify it, and it's the same questions to rectify the Toda. It's the same question when we have this kind of cube. Sorry. Yeah. It's the same to rectify if you have, sorry, here H, if you have the situation of the Toda, is the same to you is that you have here not a commutative square, but homotopy commutative square, and here another homotopy commutative square here. You see this side, this side. So it's the same question for the Toda. So this specific one we can't always rectifying. So the general one we can always rectifying, but the obstruction for rectifying is generalization of the Toda, but in another way, not longer. It's because if you choose a null homotopy here, you choose, for example, for this null homotopy, and you compose with the last one, so you get a map, okay, from X, I to D, okay? And you can choose a null homotopy for this side, for example, this side, okay? Null homotopy, another null homotopy, for example, F, oh, sorry, I don't, and you can, and you then get from X, I to, and you compose, sorry, compose this with the last one, with this map, and you get another map from X cross I to D. And you can also, you can do it here. You can choose a null homotopy here, and you compose with this map now. Okay, with this null homotopy, and you get, but there is some sides, common sides for them. Okay, so you get this thing. You get this thing. So if you can fill it, if you can choose higher order to null homotopy, that you can, if you can fill it, so you can rectify. If not, no, you can't. Okay. So the Toda bracket, it's when we have just two sides and the other points. Okay, we have this the Toda bracket here, point and this in this case. Okay, in this case. So we have this, and if we can fill it by double cone or by something that the Toda is the same to say that the Toda is null homotopic. This map is null homotopic. Okay. So then we can rectify. So we have the same here. It's a special case of this. Okay.
So in your category, the objects are fibrant and cofibrant, so that these kind of homotopies correspond to weak equivalences, I guess.
I didn't do that in my category. No, it's just a pointed model category. It's you can, and I did the replacement when I all the time choose because I did the diagrammatic. You know, I can back there because I have. Yeah. Here, it's enough. It's enough. You know, if you have, for example, double the case where you have four maps and null homotopies. So you have this diagram, but not everything is cofibration. No, it's just object, okay, and maps, okay. But you can't what?
I mean, the objects are fibrant.
No, you don't need. But you can replace for every Toda system. You know what I mean by Toda system? It's all the maps.
You can
the null homotopies, the second order null homotopies, maybe more if you have a longer sequence. So you have this diagram, okay, which encode all the information, okay. So here maybe I wrote everything cofibration, but suppose you don't have anything. All the object is it's just object and maps. You don't know if it's, but you can do replacement, a cofibrant replacement. but with the same shape. Yeah, you stay with the same Okay, you can replace this by a diagram where everything is every object here. The object is this object is cofibrant. This maps is the first cofibration. Every maps is cofibration, and you know for the push out from this to this is here. It's obvious. Maybe the push out from this to this is cofibration. So you cofibrant cube. You replace it by, you can do that. Okay. Then why I want this? Because I want to apply I want to know that if I apply the homotopy cofiber or the cofiber itself, the cofiber, the real cofiber, the kernel. Okay, if I apply this, it's the same like the homotopy cofiber. But it's not true in any model category. You know, in any pointed model category, it's true. You must have the proper property. You know.
Okay.
Well, yeah, you have to. It's topological spaces. It's okay. Simplicial sets, chain complexes. It's okay. We have this property when the if you replace your diagram by cofibrant, okay, cofibrant one, so then the cofiber of this diagram and the homotopy cofiber is the same. It's not exactly the proper, but it's induced by the proper. It's a proper, yeah.
Okay, thank you.
Thank you for your questions.
So, are there any other questions? Okay, thank you again.
Okay, thank you very much. Thank you, everyone. And sorry again. Okay, for everything. Okay. Bye bye. Bye. Thank you.
Bye. Thank you.
Bye.
Thanks.
Bye. Bye, Red. Bye.
See you.